Hi everyone, and welcome back to the MCAT A series of lectures in physics. In the previous lesson, I introduced the idea of the electric field. Any static charge, in other words a charge that is not moving, creates its own electric field. If such a charge is also moving, then it creates an additional field known as a magnetic field. Such a field will be the discussion of this short video. In this lesson, I shall describe in more detail what a magnetic field is, as well as describe the motion of charged particles within a magnetic field, that is, how a particle reacts to the force on it caused by the magnetic field. As I just stated, any moving charge creates a magnetic field. Such magnetic fields can be created, for example, by individual charges such as a proton or an electron, or by a collection of moving charges such as a current, and a current will be described in more detail in the next lesson. As we also know from our everyday lives, there are such things as permanent magnets, for example fridge magnets, which are created by what is known as magnetic spin. The details of permanent magnets are outside the scope of the MCAT. What you do need to know, however, is details about magnetic fields created by moving charges. The unit for magnetic field strength is the Tesla. It is a derived unit and is equivalent to 1 Newton-second per meter coulomb. Again, as I just said, any moving charged particles create a magnetic field. Therefore, a collection of moving particles such as that through a wire will certainly create a magnetic field. We can therefore quantify what the magnetic field strength is for a wire. I will discuss in more detail in the next lesson what a current is, but roughly a current is simply a flow of charge. It is the amount of charge per unit time. Therefore, anytime there is electricity flowing through a wire, there is a current. In this wire I have drawn here, that current could be pointing up or down. In this case, let's assume that that current is pointing up. It turns out that the magnetic field created by such a current has a pattern as I have drawn here. I have drawn this using, again, field lines, magnetic field lines in this case. As you can see, these magnetic field lines form a loop, in this case a circle. In general, magnetic field lines always form a loop. If you recall from our last lesson, electric field lines, for example from one charge, radiate outwards. They do not meet again at some point. In contrast, magnetic field lines always join back up with themselves. Here also we see that the magnetic field lines have a direction counterclockwise around a wire. This is purely due to the direction of the current. If the current was instead going down the wire, the magnetic field line direction would instead be clockwise. Determining this direction can be done simply by using what is known as the right-hand grip rule. To see this, take your right hand and give yourself a thumbs up. Your thumb is pointing in the direction of the current, and the direction of your fingers are pointing in the direction of the magnetic field. They are wrapping around in a counterclockwise fashion. If you instead give yourself a thumbs down with your right hand, then your fingers are pointing clockwise. They are wrapping around in a clockwise fashion. That would be the direction of magnetic field lines if the current was instead pointing down. Also, and I have not really shown this too well in this diagram, but as you get further from the wire, the distance between the magnetic field lines increases. That is, the distance between two magnetic field lines that are next to each other is growing as you increase your distance from the wire. Recalling from the last video that I stated that how close the field lines are together describes how strong the field is, then the increasing separation with field lines with increasing distance from the wire means that the magnetic field strength is decreasing with increasing distance from the wire. In other words, the magnetic field length is strongest the closer to the wire. If we assume that the wire is infinitely long, then we can actually quantify what the magnetic field strength is for a particular current and a particular distance from the wire. This is given as follows. The magnetic field strength is equal to a constant μ0 multiplied by the current I divided by 2 multiplied by pi multiplied by the distance from the wire or. μ0 is known as the permeability of free space, and it is equal to 4 pi multiplied by 10 to the minus 7 Tesla meters per amp. Again, these units come from rearranging this equation for μ0. If you rearrange this equation for mu0, you will find that the units are Tesla meter per amp. I have not defined what an amp is, but an amp is simply the unit for current. I will go into more detail about this in the next lesson. This situation is one of two situations that you need to know for the MCAT regarding strength of magnetic fields. The other is that of a circular loop of wire. What I mean by this is the following. We just considered a straight wire, but now we're going to bend that wire into a circle. I have a current going through this wire, but then I have the wire bending into a circle. As I have the current going up on the left, this current goes clockwise in this situation. In the previous case, I had the magnetic field lines being circles around the wire. In this case, however, the magnetic field lines instead point either into or out of the screen. Such field lines are of course very hard to draw because they exist in this third dimension. Instead, I will use crosses as I have shown here to represent magnetic field lines that are going into the page. Magnetic field lines out of the page are instead represented by circles with dots. Therefore, in this situation with a circular loop and a current going clockwise, the magnetic field lines point into the page. If instead the current was going counterclockwise around the loop, in other words from right to left, the magnetic field lines would instead be pointing out of the page. Again, we can quantify the magnetic field strength B inside this loop. In this case, we can only do it inside the loop, we can't do it on the outside away from the loop. Inside the loop, the magnetic field strength is given as follows. The magnetic field strength B is equal to, again, this constant mu0 multiplied by the current in the wire I divided by 2 multiplied by simply or, where or is the radius of the circular loop. What this is telling us is that the magnetic field strength within the loop where I've drawn those crosses is equal everywhere. Everywhere inside that circle, the magnetic field strength is the same. I have just described the two different ways that magnetic fields can be created. These are the only two ways you need to know for the MCAT. Now I would like to assume that we've created these magnetic fields and describe what happens when a charged particle enters such a magnetic field. That is, we already have a magnetic field created by particles or by a particle or by a collection of particles and so on, and then we introduce a test charge. It turns out that a charge placed in a magnetic field will experience a force. It will be accelerated due to the fact that it is in this magnetic field. To quantify this, let us look at one particular example. Let's assume that we have a background magnetic field B pointing downwards. Again, this magnetic field could be created by a wire that I have not shown. Let us also assume that we have a test charge Q moving to the right with a velocity v. This test charge will experience a force due to the presence of this magnetic field given as follows. That magnetic force F is equal to the magnitude of the charge Q multiplied by the cross product of the charge's velocity v and the magnetic field B. Of course, we already know that velocity is a vector, but magnetic field must also be a vector since it has a direction. In this case, that direction is downwards. Recalling what is meant by the cross product, this means that the magnetic force is equal to, again, the charge multiplied by the magnitude of the velocity, multiplied by the magnitude of the magnetic field, multiplied by the sine of the angle between the magnetic field and the velocity vectors. In this case, that angle is simply 90 since the velocity vector is pointing to the right and the magnetic field is pointing downwards. Sine of 90 is equal to 1. And therefore in this case the magnetic force is simply QVB. It is simply equal to the charge multiplied by the velocity multiplied by the magnetic field. However, of course, in general, the velocity vector and the magnetic field vector could be at more complicated angles. For example, instead of having the particle entering to the right here, I could have it entering at an angle of, say, 30 degrees to the horizontal. Note also that if that test charge particle was moving in the same direction as the magnetic field, in other words the velocity and the magnetic field vectors were parallel, then the force on that particle would be zero. There would be no force on it due to the magnetic field. This is because the angle between the velocity and magnetic field vectors are zero, and since sine of 0 is equal to 0, the magnetic force must be 0. That cross product would be 0. I have just shown you how to calculate the magnitude of the force, but remember, force is a vector. It must also have a direction. How do we work out the direction? Well, again, we have a hand rule, in this case a right-hand rule, for determining the direction of the force. Again, if we take our right hand, with the velocity vector pointing in the direction of our first finger, the finger next to the thumb, and our second finger pointing in the direction of the magnetic field, then our thumb is pointing in the direction of this magnetic force. This means that for the situation I've drawn here, and you might have to wriggle your wrist a bit in order to get this situation set up, but if you do it correctly, you will see that the force on this particle points into the screen. This means that this particle is going to be accelerated into the screen. It's going to be accelerated into that third dimension. What is the size of that force? Well, it depends on the magnitude of the velocity and the magnetic field vectors. As a quick example, let's assume that the velocity has a magnitude of 1 meters per second and that the magnetic field strength is simply 2 Tesla. Let us also assume that the particle is simply a proton. It is a particle of charge plus E. It has a charge of 1.6 multiplied by 10 to the minus 19 coulombs. Therefore, the magnetic force on this particle is equal to Q, which as I said is 1.6 multiplied by 10 to the minus 19, multiplied by the magnitude of the velocity, which in this case is simply 1 meters per second, multiplied by the magnitude of the magnetic field strength, which in this case is simply 2 Tesla. Working this out, we get that magnetic force is equal to 3.2 multiplied by 10 to the minus 19 newtons. And again, as I stressed in this case, that force is pointing into the screen. That force is causing that charged particle to accelerate into the screen. A neat result comes about from considering a charged particle within such a uniform magnetic field. To visualize this easily, let me instead consider a magnetic field that is pointing into the page. To represent this, as I already mentioned, I will use crosses to represent fields into the page. Allow me to also assume that the particle is positively charged and it is initially moving upwards. In other words, it has a velocity pointing up. If you use the right-hand rule correctly, and I urge you to check it, you will find that the magnetic force on this particle is pointing to the left. What is the resulting motion of the particle? Well, the particle was originally moving upwards, but it is now accelerating to the left. This therefore means that as it moves upwards, it starts curving to the left. Therefore, overall, its velocity vector gets shifted slightly to the left. We can then apply the same logic again, and we will see that that velocity vector moves even more to the left at the next instance. If we continue along this fashion, overall, we will see that this charged particle moves in a circle. We can actually see this quite easily without even using the right-hand rule. If we look at the diagram as I have drawn it, we have a particle moving with a velocity v upwards, and there is a force being applied perpendicularly to that velocity. This is very similar to the motion of an object moving in a circle that we saw earlier. Such an object had a velocity that was tangent to the circle, and it had a centripetal force as well as a centripetal acceleration pointing towards the center of the circle. This is exactly the situation we have here, and therefore this particle must move in a circle. Therefore, in general, a charged particle moving in a uniform background magnetic field will move in a circle. In the MCAT, it can be quite common to be given such a diagram and be asked what will change if one of the quantities within this diagram changes. For example, the velocity vector could instead be pointing down, or the particle could instead be an electron and therefore have a negative charge. I encourage you to try different situations and make sure that you understand what happens when certain things are changed in this diagram. Also, remember, in general, there is also an electrostatic force associated with each particle. Hence, for every particle, there can be both an electrostatic force and a magnetic force. The sum of these two forces is known as the Lorentz force. The Lorentz force is equal to the sum of the electric and magnetic forces acting on a charged particle. Finishing off this lesson, I have just looked at the magnetic force on a single test charge. Now I would like to look at the magnetic force on a collection of charges, in other words a current in a background magnetic field. For example, I could have a situation as follows. I have a wire with a current I going through it, and in this case I have that current going to the right, and a background magnetic field B. Since there is a magnetic force on one charge, there must also be a magnetic force on a collection of charges. The strength of that magnetic force is given as follows. It is equal to the length of the wire capital L multiplied by the cross product of the current and the magnetic field. Again, both current and magnetic field are vectors as they have direction associated with them. I use arrows to represent them on a diagram. As before, recalling that cross product is simply the product of the magnitudes multiplied by the sine of the angle between the vectors, we can also write this as the length of the wire capital L multiplied by the magnitude of the current I multiplied by the magnitude of the magnetic field B multiplied by the sine of the angle between the current vector and the magnetic field vector. It turns out that we can use the exact same right-hand rule that I just used for a single charge. This right-hand rule can be used to calculate the direction of the magnetic force. As you may guess by the length of this video, there is not much material on the MCAT about magnetism. Therefore, it would be very good for you if you feel confident dealing with such a small topic for the MCAT. Let us test this confidence by, as always, looking at some questions that are of similar standard to the MCAT. The first question is testing the use of this right-hand rule that I introduced. The question states that we have an electron, in other words a negatively charged particle, moving up the page in a background magnetic field. That background magnetic field is pointing to the left. The question then asks us what is the direction of the magnetic force on the electron. Is it to the right, is it into the page, is it down the page, or is there no magnetic force on the electron? Well, we know immediately that since this is a charged particle, there could be a magnetic force. As long as the velocity vector is not parallel to the magnetic field vector, there will be a magnetic force on the charged particle. To visualize what is happening, let us draw a quick diagram. We are told that we are given an electron, in other words a negatively charged particle as I have drawn here, and that it is initially moving up. It has a velocity vector pointing up. We are also told that the background magnetic field points to the left as I have shown here. As I described previously, if you take the first finger on your right hand and point it upwards, and take the second finger on your right hand and point it to the right, your thumb will point in the direction of the magnetic force. If you do it correctly, you will find that the magnetic force must point into the page. This therefore means that the correct answer is option B. As I stressed earlier, you should test to see what happens if you, for example, change this from an electron to a proton, have the velocity vector point down or left or right, or change the direction of the magnetic field, have the magnetic field point to the right or into the page, and so on. The final question is testing our knowledge about the magnetic field created by a straight wire. We are asked in which of the following cases is the magnetic field strength the greatest? Is it at a distance of 20 centimeters from a wire carrying a current of 2 amps, a distance of 5 meters with a current of 100 milliamps, a distance of 80 centimeters with a current of 1 amp, or a distance of 3 centimeters with a current of 500 milliamps? Well, let us recall what the formula is for the magnetic field created by a straight wire. The magnetic field strength B is given as follows. It is equal to a constant mu0 multiplied by the current I divided by 2 pi multiplied by the distance from the wire or. Hence, as we want to compare different values for different currents and distances, we are only concerned with the I divided by the orbit. The mu0 over 2 pi will remain the same. These are simply constants. We want to figure out in which of these 4 cases is I divided by or the largest. To do this, I will use the currents in amps and the distances in meters. I can of course use other units, but whatever units I use, I have to use those same units in all 4 cases. For the first case, I have that the current is 2 amps and the distance is 20 centimeters or 0.2 meters. Therefore, this factor I divided by R is going to be equal to 2 divided by 0.2. In other words, this factor is 10. For the second case, this I divided by R is going to be 100 milliamps, which is 0.1 amps, divided by 5 meters. 0.1 divided by 5, which is equal to 0.02. Next, I divided by R is given by 1 amp divided by 80 centimeters. 1 divided by 0.8 meters, which is equal to 1.25. Finally, I divided by R for the last case is equal to 500 milliamps or 0.5 amps divided by 3 centimeters divided by 0.03 meters. Working this out, this is equal to 16.666 and so on, or roughly 16.67. Therefore, we see that this factor is greatest in option D. Therefore, the correct answer is option D. This video served as a brief introduction to the idea of magnetism. Remember, any charge, moving or not moving, creates an electric field. If that charge is also moving, then it creates an additional field known as a magnetic field. We use the symbol B to represent that field, and it has units of Tesla. We then looked at the magnetic field created in two different situations: the magnetic field created by a straight wire and the magnetic field created by a loop of wire. For a straight wire carrying a current capital I, the magnetic field strength at distance r from that wire was given as μ0I over 2 pi r. For a loop of wire again carrying a current capital I, the magnetic field strength inside that loop and only inside that loop is given as follows. It is equal to μ0I divided by 2r, where r is the radius of the loop. I then described that a charged particle entering a magnetic field, and this magnetic field could be created by other charges, causes a force to be exerted on that particle. This is the case as long as that particle is charged and as long as that particle is not moving parallel to the direction of the magnetic field. The magnitude of that force is simply equal to the charge on the particle Q multiplied by the magnitude of the velocity v multiplied by the magnitude of the magnetic field B multiplied by the sine of the angle between the velocity and the magnetic field vectors. This magnetic force is therefore maximum when the angle between the velocity and the magnetic field vectors is 90 degrees. It decreases towards a minimum as this angle converges to 0. I also stated that this magnetic force is the magnetic component of the Lorentz force. The Lorentz force is the sum of the electrostatic force and the magnetic force. Finally, I also looked at the magnetic force on a wire when it is likewise placed inside a magnetic field. For a wire of length L with a current I passing through it, the magnetic force is equal to the length of the wire capital L multiplied by the magnitude of the current I multiplied by the magnitude of the magnetic field B multiplied by the sine of the angle between the current and the magnetic field vectors. I finished by emphasizing the fact that you can use the same right-hand rule for both a single particle placed in a magnetic field as well as a wire placed in a magnetic field. As I emphasized, there is not too much variation as to what can come up on the MCAT about magnetism. Therefore, please ensure that you understand these basics that I have introduced before moving on to the next video about electric circuits. As always, I hope this video has been useful to you, and I shall see you guys in the next one.